Okay, so welcome back to Physics 1A for February 24th. This is the first hour. Today we're going to be continuing to talk about vector and scalar products. Then we're going to talk about the first condition of equilibrium. And if we have time, we'll talk about friction. And almost entirely what we'll be doing today is just solving a lot of problems. So this lecture might be kind of dense. It might be kind of thing where you might want to go back and rewatch things if there's stuff you miss. But I highly recommend that you ask questions if you have them. Okay. So last time we talked about the scalar product. I'll remind you what it was. So we call it the dot product or the scalar product. And the way we define it, I'll just put it here. This is also a scalar product. It's called that because it takes two vectors and it turns them into a scalar via multiplication. And the way that we generally define it is you've got some vector A here, you've got some vector B here, and they're separated by an angle theta. And you can say that we define the cross product or the dot product to be A dot B, use a dot, not an asterisk or anything like that, is equal to the magnitude of A times the magnitude of B times the cosine of the angle between them. That's it. Remember that if I have a vector and I write it like with just an A, I mean magnitude. There's two different ways to do that. So you can write magnitude by putting two bars around it. That just means the length of the vector. Or the other way to do it is just to write the vector without a vector symbol above it. And that means the magnitude of the vector. So this corresponds to magnitude. Magnitude, again, means size or length, whatever you want to do. Now we also learned another definition of the dot product, which is we know that any vector A, for example, can be written in unit vector notation like this. Okay, so any vector can be written like this. So for example, a vector that we may have used last time may have been something like 3i hat plus 2j hat minus 5k hat, for example. Right, so you basically, in this case, you're writing the x component here times I hat, y component times j hat, z component times k hat. Okay? So if we write it like that, it turns out that this definition of the dot product can be written like this. If you just multiply the x component of one times the x component of the other, and then go through and do the same thing for each of the other components, this is your other definition of what the dot product is. So let's do two problems with this. This one and this one. Oh, wait, combine them. I don't want to combine them. We'll just do them one at a time then. Oh, where'd they go? Alright. And we can go full screen here too if we want to. So here's the problem we want to try to do. It's very straightforward. It says, find the scalar product A dot B of the two vectors in figure 128. So I've got a vector A pointing this way at an angle of 53 degrees relative to the x-axis, and a vector B, which is pointing off at a much larger 130 degrees relative to the x-axis. And it tells us that the length of A is 4, the length of B is 5, and we want to calculate what is A dot B equal to. Well, it's going to be equal to the length of A, which they're telling us is 4. There's no units here. Multiplied by the length of B, which they're telling us is 5. And then I need to multiply by the cosine of the angle that is in between them. So on our picture here, what is that angle going to be? Can anyone type in the chat? What's the angle we're going to use going to be if I want the angle that's included between the two vectors? Is it going to be 53, 130? Is it going to be something else? All right, 77. And you all got that because it's the difference between 130 and 53, right? So it's going to be the cosine of 77, which again is 130 degrees minus 53 degrees. That's this angle here, which is labeled, I think, as phi. I can't tell if phi is supposed to be this angle or if it's the whole angle, but 77. Okay, and then we just calculate that, right? It'd be 45 times whatever the cosine, or 20 times cosine 77. I got 4.5. Yep. There you go. And again, notice that this would have units. These, I don't like problems that don't have units, but it's just kind of a math problem, so I guess it's okay. 4.5. And again, you have vectors here, and this is a scalar, so that's why we call it the scalar product. All right, let's do one that's a little trickier. Okay, this one says find the angle between the vectors. And we're given two vectors, 2i hat, 3j hat. Let's write these over here. And it just says find the angle between the vectors. We're gonna do one other thing. We're gonna find the angle that vector A makes with the x-axis. But how do we do this first part? We'll call this part A. How can I find the angle between the vectors? Find the magnitude of A and B, Robert says. Okay, that would be something we could start with. What else do we need to do? What's our general strategy here going to be? To find the angle between the vectors. Calculate the dot product and then solve for theta. Yeah, that's pretty much right. That's pretty much right. Okay, so we know that the dot product contains within it an angle. And that angle represents the angle between the vectors. So if we can calculate what A dot B is, and then if we can calculate the magnitude of A and the magnitude of B, as someone mentioned, then the angle theta is going to be sitting right there, right? And if we then just solve for the angle, yeah, Summer says divide the scalar product by the product of the magnitude of two vectors. Yeah, pretty much. We're gonna take A dot B, and we're going to divide by A times B, and that should be cos theta, and then we can inverse solve for cos theta by using a inverse trig function, right? Okay, so we need to do all these things. We have to find A dot B, we have to find the magnitude of A, find the magnitude of B. Let's start off with magnitudes. How do I find the magnitude of a vector that has 3 components? How do I find the magnitude of a vector that has 3 components? Josby, so one person had said that you could use the x and y components to find the angle. Unfortunately, that won't work. We can talk about why. Okay, so someone said basically we're going to square each of these. So 2 squared plus 3 squared plus, this is a 1 here, 1 squared. And then if we square root that, that should be the magnitude of the vector. That's exactly right. So this is like an extension of the Pythagorean theorem into 3 dimensions. And that's how it works. Just square the components. Okay, so we'll get an answer for that. I think we'll probably just leave it as a square root. So it's going to be the square root of 4 plus 9 plus 1. What is that? 14? Square root of 14. And then we'll come over here with b, and we'll do the same thing. So it's going to be 4 squared plus 2 squared plus negative 1 squared. Now technically it's negative 4 squared, but the negative sign will square away. Same thing here. And that should give us the magnitude of b. Sorry, I should put bars on that to indicate that we're doing magnitude. 16 plus 4 is 20, plus 1 is 21. Okay. Any questions about that? Sorry. I'm trying to get this unit to stop making noise. How did you know to approach it by squaring it? Well, how much do I want to explain? So you know that if you have a vector that's in 2 dimensions that has, for example, an x component here and a y component here, that if you want to find the magnitude of the vector, you can use the Pythagorean theorem, right, Andrew? r squared is equal to x squared plus y squared. It's the same thing. It's the same thing. Because now what you need to do is you have to add a third dimension, and I can't guarantee you I can actually draw a third dimension on here, but what I'll try to do it. So suppose you have a z coordinate coming out this way. Now, what happens here? That's actually a bad place to draw it. Let me undo that. I think it might be a little easier to see if I draw it here. So let's say you have a z coordinate coming out this way. It's not going to be obvious. These two are going to have to make a right angle with each other, right? Any vector that I draw in the z direction is perpendicular to the plane xy, right? Which means it's also perpendicular to this vector right here. This looks awful because it just doesn't, but I could exaggerate it some. Like if I make the z coordinate come kind of off that way, it's not going to be good. I'm not good at drawing in three directions. Point is that after combining these together, if I make another perpendicular, maybe that's a little bit better, z. This is automatically perpendicular to this. And now if I think of a... We now have a new right triangle where one side is r and one side is z, basically. I guess, like, you know. Okay, you understand. Good. That was not the best explanation. I apologize. I do a lot better with this stuff on a chalkboard, honestly, but anyway. We don't have that right now. All right, this is what we need to do now. We need to find, we found A and we found B. We need to find A dot B, right? So let's do that. So our definition for A dot B in the case where we have unit vectors given is that we're going to take this times this. You multiply the x components, so we have 2 times negative 4. And then we add to that, multiply the y components by each other, 3 times 2. And then 1 times negative 1. Okay. So we'll get negative 8 plus 6 minus 1. I think that'll be negative 3. Anyone disagree? So then we have this equation right here, which tells us that the cosine of theta now has to be equal to A dot B, which is negative 3, divided by A times B. Like that. And then we can use that to solve for the angle, because then the angle is going to be cosine inverse of negative 3. You need to leave the negative sign in there too. So I have a question before I get the answer here. Do you expect this angle to be between 0 and 90 or greater? If you think about it, if you take any two lines, right? So I take a line this way and I take a line, let's say, off this way. Then really the biggest that the angle between the two of them could be would be 180 degrees, right? So the angle between two vectors could either be acute, between 0 and 90, or it can be obtuse, between 90 and 180. And you're all saying it's going to be greater than 90 degrees. How do you know that before you calculate it? How do you know it's going to be greater before you calculate it? Yeah, the negative sign, exactly. So what I get if I plug all that stuff into a calculator is 100. And that's the reason I ask is, do you think it's going to be between 90 and... Do you think it's going to be acute or obtuse, basically? Is it because you need to know kind of before you do a calculation to make sure that you actually... the answer makes any sense? So, yeah, we got an answer that makes sense, basically. It's good to make a prediction before you actually do a calculation, because we can all make mistakes when we put things in calculators, and maybe I made a mistake. You tell me, is that right or wrong?
How can you tell if it's acute or abused?
Okay, so if the dot product is positive, it's going to be acute. If the dot product is negative, it's going to be obtuse. That's how you can tell. You got the same, you got 100 degrees, good. You're kind of lost, Andrew? What are you lost about? Andrew, I see your mic's cute, but I don't hear anything. I don't know if you're trying to talk. But if you could tell me more about what you're lost on. We haven't done part B, by the way. All we did so far is this. We still have to do this. So I'll answer that question in a second, Hanif. Find the angle that A makes with each axis. We're going to do that next. Okay. All right, Andrew. I'll let you type. I haven't seen you finish what you're writing yet, but we'll come back. Okay. How do I do this? How do I find the angle that A makes with each axis? So let's start off by finding the following. What is the angle between...
Can you hear me now?
I can.
Whenever you have time, I can answer the
Go ahead.
the question.
Go ahead, I'm waiting.
So basically, all I'm confused about is basically the dot product equation from vector A times vector B, and then you get...
It's not vector A times vector B. I apologize to interrupt. It's A dot B, or the scalar product. It's not the same thing as multiplication. Anyway, go ahead.
Okay. So dot product A, it's not the same as multiplication, right? So it's not multiply dot product B, right? How would you say that then?
Just A dot B. We usually
now.
say A dot B.
Okay, so A dot B is equal to 2 times -4. How'd you get the -4? That's where I'm confused
So
about.
we're doing, basically we're taking this 2 times this -4 right here. You multiply the x component of A times the x component of B. That's the first term here. I could write it like this. It's basically A sub x times B sub x. And then we did A sub y times B sub y. Yeah, I could have written the equation out. That would have probably been a lot more clear. Okay, does that make sense?
Yeah, that made total sense. I see where you got that now. Okay.
Good. Okay.
And then you just plugged in the formula for cosine, and then you just did the inverse property of cosine to get...
Yeah, just using our definition of the dot product. Okay, what's your question, Hanif? Okay, and Googleplex is answering part B. I'll go ahead and say that's right. You're saying that in order to find the angle between vector A and the x-axis, we could just find the angle between vector A and the I-hat, which would involve doing this. You're saying basically if you do A dot I-hat, right? And then that's equal to A times the magnitude of I-hat, which is 1, and then times the cosine of the angle between them. I'll call this theta sub x. And that's what we'll solve for. Okay, Hanif says, you say it's not the same as multiplication, but it looks the same to me. What's the difference? Let me just come down here a little bit and I'll show you something. Suppose that I had the following expression, 5x plus 3y plus 2z, and I wanted to multiply this times another polynomial like 2x plus y plus z. Right? So in order to do this multiplication, there's going to be a total of 9 terms. I have to do 5x times 2x, I have to do 5x times y, I have to do 5x times z, and then I have to do 3y times 2x, and I have to do 3y times y, and I have to do 3y times z, and there's 6 more. So do you see the difference? Okay. Good question. Okay. So in order to find the angle between vector A and the x-axis, we're going to be using this operation. We're going to say the x-axis is represented by I-hat. That's, again, the unit vector, a vector of length 1 that points along the x-axis. And we just do A dot I-hat, and that should be equal to this. And that should give us the angle, theta x, between vector A and the x-axis. And I can't even really draw that on this picture, because vector A kind of points up at an angle to all the axes. So we'll have to just do this mathematically. So vector A is written up here at the top. If I do A dot I-hat, I can tell you that what I'm going to get. Can you tell me what am I going to get? What is this going to be? What's A dot I-hat going to be equal to? It's 2. That's exactly right. Because if I do... Remember, these are the things you have to remember. I-hat dot I-hat is 1, but I-hat dot J-hat is 0, because the angle between these two is 90, and I-hat dot K-hat is also 0. So that means that if I do... Let's write the whole thing out. It's 2, 3, 1, right? Okay. So what we're doing is 2 I-hat plus 3 J-hat plus 1 K-hat. And we're dot producting that with I-hat, right? And so what I'm saying is you're going to get 2 I dot I, which is going to be 2, and then 2 I dot j, which is going to be 0. Oh, sorry, my bad. Let's say that again. In fact, I should just not skip steps. This is physics 1a. You have to assume that I really should show all the steps. So 2 I dot I plus 3 j dot I plus 1 k dot I. But the thing is that these are all 0, according to these definitions here. So that means that the answer is 2. So we get 2 equals, magnitude of A was root 14, right? Yeah. Square root 14. And then that's multiplied by cosine of the angle that vector A makes with the x-axis. And we can then solve this. So we'll get cosine inverse of 2 divided by square root 14. And that's going to be equal to theta sub x. Let's see what that is. Should this be between 0 and 90? Should it be acute or should it be obtuse? What do we expect? Yep, acute because the dot product's positive, right? I got 57.7 degrees. And it's like 57.688, so I'm around to 57.7. So there we go. That's how we find the angle with the x-axis. Let's do one more, and I'll let you do the other one yourself. If I want to find the angle that vector A, and please, if you have questions, go ahead and type them in the chat. If I want to find the angle between A and the y-axis, then I need to do... What do I do? With j hat, exactly. So we'll do a dot j hat. Can you tell me what a dot j hat's going to give us? It's just 3, right? It's just going to be that one. Because that's the only one that's got a j in it. So this is going to be 3. And then that's equal to a, which is root 14, times the cosine of theta y. And then we can solve theta y by doing inverse cosine of 3 over root 14. Getting kind of low on the screen here. This then should be equal to, again, it's going to be acute because the dot product is positive. Okay, so you've got some problems on the lab manual homework as well as on your regular homework, I believe, that are going to ask questions like this. And it really just comes back to using the dot product. This gives us 36.7. And you could go on and find the angle with the z-axis if you want to by using k hat. Yep, that's right, Googleplex. If you want to use the negative y-axis, you would use negative j hat. That's exactly right. That's right.
Which one wrote up?
What's up?
Is the a vector times the is that that's a dot product, correct?
This is a dot product. This is a dot product. Yeah.
Okay, yeah, I just want to confirm.
Okay. I'll tell you something else that you can use to know that it's a dot product. I can't write things like this, for example. If I write a and then use the normal times sign and put a b in here, this is not defined. Okay? The only things that are defined are a dot, if you have two vectors at least, when you're multiplying two vectors, you can, only so far we have is the dot product. We're going to learn the cross product next. It's 2:30. Okay, let's keep going. Oh, we'll define it first and then we'll do the problem. Okay, so the next thing we want to define is what is called the vector product or the cross product. This one's a little trickier. These are the same thing. Okay. So this one is defined in the following sense. This requires 3 dimensions for a definition. So I will do my best to draw on this. Oh, what we can do is pull a little XYZ axis right here. Okay, so let's say that I have two vectors that are drawn into, oh well, let's use the XZ plane, okay? So that's gonna be hard to do. We'll use the XY plane to draw some vectors. So let's say that I have two vectors that are drawn, and let's say one of them lies just nicely along the x-axis like this, and we call it vector A. and then I have another one that goes pretty close to the y-axis. But let's say that both of these vectors are in the xy plane, okay? No, Hudson, that's fine. That's not a problem. You just needed to be here at the beginning. So if you need to go to your dentist appointment, go ahead and go. Yeah. Okay, so let's say we have vector A, vector B. They are both in the xy plane, right? That's important. And let's use the angle between the two of them, and let's call it phi. Then we can define another type of vector, another type of product with a cross sign like this, and we call this the cross product. And one definition of it is that the magnitude of it, at the very least, is going to be equal to AB times the sine of phi. But that's just the magnitude, okay? That's just the size of the vector, is AB sine theta. It also has a direction. It turns out that this vector, which, what I'll do is, here. No, I think that's how I want to write that. What I'm also going to do is just say, let's call A cross B. It turns out this is going to give us a vector as an answer. So let's call it C. And I'm just going to say that that vector C is going to turn out, it's going to point right along the z-axis, actually. Perpendicular to both vectors, basically. So that is A cross B direction. So there's two things. This is the magnitude. And this is the direction. And the way we find the direction is by using something that's called the right-hand rule. I'll explain what that is. Or I'll do my best. So magnitude is just AB sine phi. Direction is given by the right-hand rule. Now the way that you do this, try to show this. I don't know if you're going to be able to see my hand very well. Let me click on this so I can actually see what I'm showing you. So here's my hand. Here's what you do. This one's kind of hard. So you're going to point the fingers of your hand. Ow, this really hurts. Should I just stand up? My hands get kind of cramped from using this stylus, but... So you're going to point the fingers of your right hand along A, and then you're going to wrap your fingers from A to B like that, and your thumb is going to point in the direction outwards, out of the page of vector C. Let's do that again. You take your right hand, you point along A, you wrap your fingers from A up to B. Oh, I think I'm inverted. I'm inverted, right? Yeah, I'm kind of inverted. So if I want to do this, I can't do it the way you guys will see it, but... Yeah, the camera's not helping with this very much. Point is that you're going to point the fingers... I'm going to just draw on the picture, I guess. I don't know. Really, you got to try to do it yourself. You cannot use your left hand. You have to use your right hand, Andrew. You have to use your right hand. The easiest way for me to do this would be to turn around, but... see if you can do it yourselves. So, take the fingers of your hand and point them along A, which is along the positive x-axis, and literally all of you should do this. Okay? Point the fingers of your right hand along the x-axis, and then rotate them up towards B, which is where the y-axis is. Your thumb should be pointing out of the board. Did that make any sense?
Yeah, it did.
Okay.
Hi, Professor. Sorry, I don't know if you saw my message, but I meant to let you know earlier that
Stop, please stop. I got your message, dude. Your mic is, I want to plug it back in. Anytime you show up late to class, then you just tell me at the break, okay? Don't tell me during class. All right, rotate your hand from A to B, and then your thumb will point in the direction of A cross B. So this is a lot harder. It's a lot harder than the dot product. Without a doubt, it's a lot harder because it doesn't just have a magnitude, it also has a direction, and the direction is given by this right-hand rule. Now, something no one has asked yet, but K hat. That's right, Louis. That'd be K hat in this case, right? Yeah. So the vector product is something where you multiply two vectors together and the answer is a vector. The scalar product, you multiply two vectors together and the answer is a scalar. That's why we call them vector product and scalar product. Hopefully this makes sense to you. If you aren't sitting at your desk and trying to do this, then I don't know why. You need to give it a shot. You won't learn this by just listening or reading. You got to actually prove to yourself that you can do this. Yeah. I could ask the following questions too. What if I, now that I have this other vector drawn on here, what if I ask the following question? What direction does A cross C point? What do you get if you do A cross C? What direction is that point? It's not towards B. That's wrong. It is along the y-axis. I see some people saying j hat, but that's not technically the right answer. It's down. It's negative j hat. That's exactly right. It's negative j hat. So A cross C would go this way. Can anyone tell me without actually, or just really quickly, I'm going to ask a question, answer as fast as you can. What direction does C cross A point then? It's positive y, right? So C cross A would be positive. Because you just do it the other way, right? You go from C to A, and your thumb points up, right? Okay. Do you all understand? Why is this important? Wait, why does it point up, you're asking? So you have to just use your hand. This is not something that, like, you have to just do it yourself. You have to say, look, A is pointing along the x-axis. Oh, there's something else I left out. You have to rotate your hand from one vector to the other, but you do it along the shortest angle, okay? The smallest angle between the two of them. So if you just try it, point your fingers along X, go from A to C, your thumb should point down. If you go from C, point your fingers along C, and then rotate to A, your thumb should point up. Okay? We're going to use matrices, but you need to understand this too. This is more important than the matrix stuff as far as physics go, okay? Because in physics, you're going to need to understand, well, these directions with these cross products. Now, and it's something we haven't talked about is like, why are we learning this stuff? Yes, you can think of it as a clock if you want to. And, you know, counterclockwise would be out, and clockwise would be in. So in physics, we're going to use the cross product and the vector products to do things. The vector product is going to be used for torque in physics 1A. The dot product is going to be used for work. Once you get into physics 1C, the cross product is even more important because the way that the electric and magnetic field operate is they have this inherent kind of right angle nature, and there's all kinds of cross products that show up in physics 1C. So, very important in physics to understand how this works over here. Okay?
Professor, quick question.
Yeah.
How come we're using negative j and positive j? I mean, that just signifies y and negative y and positive y, right?
We use these ijk things as just it doesn't exactly mean the same thing as positive y and negative y. Yes, this does negative j points in the negative y direction and positive j points in the positive y direction, but they have the specific, like, they're length 1. They are a vector of length 1 that points in those directions, and that's useful to us. Because if you think about the way we do counting, let's do some really basic things here. When I say the number 3, you know that means 3 units of 1, right? 1, 2, 3, right? We count by ones, so as far as the natural numbers go, when I tell you a number like 150, you imagine maybe, I don't know, 150 units of 1, right? That's what we mean by that, right? Just like if I said 150 apples, it'd be, the unit would be apples, right? So if I say that I have a vector, okay, let's say that I have a vector and I call it vector D, and I tell you it has a length of 10 j hat, well, you know that's a vector that has length 10 that points in the positive y direction. And that's pretty powerful. Does that make sense, Andrew?
That makes sense. So just to clarify.
So instead of 10
J-hat is
apples,
a
right,
common-
it's 10 j's. What?
Yeah, J hat's a common thing that physicians use mainly. That's something we're gonna commonly see.
So physicians are people that do medicine. Physicists are the ones that use the j-hats. But yeah, you'll see this come up. You'll see it come up pretty commonly. There's other notation. So we're using the IJK notation. I personally do not like this one very much, but I use it because all of the physics textbooks use this, and other teachers are going to use it too. The one that I prefer is this one: x hat, y hat, and z hat. I like that better, and you'll see this. You'll see this in other physics textbooks sometimes. You'll even see some people use this one: E1, E2, and E3 hat. That's one that you see too. So, I think mathematicians prefer this one maybe because it can be kind of, you can go to multiple dimensions. And physicists sometimes want to do that too. And some of the work I did involves, extra dimensions in space. Okay, Haiti had a question of, is there any other way of finding out the direction without using the hand method? There's other methods that also kind of do the same thing, but they're all usually called the right-hand rule.
Okay.
So, yeah. All right. Negative A cross C is positive J. Yes, that's right, Louis. That's right. I'm going to do 2 problems here. We're going to do one that is really quite easy, and then we'll do one that's going to be a little trickier where we'll introduce the matrices that you all mentioned. So calculating a vector product. Okay, we have a vector. I can go a little bigger on this, right? Okay, vector A, you can see it right there pointing along the x direction. Has magnitude 6 units, is in the direction of the positive x-axis. Vector B has a magnitude of 4 units and lies in the xy plane, making an angle of 30 degrees with a positive x-axis, which is between those angles, those vectors. Find the vector product C, which is equal to A cross B. Now, they've already drawn the direction on here, but you should verify for yourself that if you rotate your hand from A to B that you get your thumb pointing along C. So, what do we have here? Well, we've got A cross B, and it is equal to the magnitude of A times the magnitude of B times the sine of phi. We've got to be really careful about how we write this because technically A cross B is a vector, so I'm just going to write this as the magnitude. So the magnitude of A cross B then is going to be equal to A, which has magnitude 6, given right there, and B was 4, so 6 multiplied by 4, and then multiplied by the sine of the angle between them. Now this one has a really nice angle of just 30 degrees, so that's handy. So we end up getting 24 sine 30, which should be 12. So the magnitude of A cross B is going to be 12, and the direction then is going to be positive k hat. So we could write that like this: A cross B is going to be 12 k hat. Really simple problem. Any questions? Yeah, Chris, that's exactly right. Counterclockwise ends up being positive, but clockwise is negative. That's true as long as you're talking about the xy plane, yeah.
How'd you know it's K hat?
Right hand rule. So point the
Oh yeah, my bad.
point the fingers of your right hand along A, rotate to B. Your thumb should point in positive Z.
Yeah, thank you. My bad.
No problem. All right, let's look at the harder way to do this, the way that you may or may not have learned in your mathematics class. Now, the next thing we want to do is we want to think about our coordinate system. And then let's draw on here our unit vectors. So we know that our unit vectors work like this. We've got I hat that goes this way, right? We've got J hat that goes this way. And then we've got K hat that comes out this way. Now what we can do is we can ask questions like the following. Andrew, I cannot slow down. We have a lot to cover today, and this is all being recorded. You can go back and you can rewatch it, and I can answer questions during the break. But I apologize. I gotta keep going. Okay, so IJK, right? Um, we can ask questions like this. What would I get if I took I cross J? Take a second to think about that. Use your right hand rule and tell me what do you get when you do I cross J? You get K hat. Make sure that you can all see that. You take your fingers. I don't know how well I can draw. I'm going to try to draw a hand just one time. Only one time, though. You take the fingers of your right hand, right? And your fingers are going to be pointing like this, with your thumb this way. And then you basically rotate those fingers up this way, and your thumb points in the K hat direction then. So if you go from I to J, picture's awful. Rotate your fingers like that, your thumb points this way, right? Okay, now you probably already know this one. Answer as fast as you can. What do you get if you do J cross I hat? Negative K hat, right? And maybe you already noticed that you always have this relationship. In fact, this is one of the properties of the cross product is that if I do A cross B, that's always equal to the opposite of B cross A. So these vectors cross products are not commutative, right? Because if I say 2 times 3, you know that's equal to 3 times 2. And if I do the same, dot products works the same way, but cross products don't. If you switch the order, it actually pulls a negative sign out in front. Okay, let's do the rest of them. There's a total of 9 combinations, right? We'll do the other ones like this. What would J cross I be? So go point your fingers along the positive y-axis, rotate to, you get negative K, yeah. No. Oh, we already did that one. I was like, wait a minute. My bad. Okay, never mind. Good. Got the right answer. Okay, what about I cross K? There we go. That's what I wanted to do. I cross K. How about that one? No. You get J. So you got to go point your fingers along I, rotate to K. What direction is your thumb pointing? Go from I to K. Is your thumb point up or down? It's negative J. That's right. Okay. Originally people were saying positive J. Your answers were coming really fast there. Negative J. That's right. What's the other one? Okay, K cross I. By the rule at the top is going to be positive J. What's the only one that's left over? I think it's JK. J cross K. What's that one going to be? This one shouldn't hurt your hands as much. Point your fingers straight up. Rotate them out. Rotate them from upwards to out of the page. Up to out. And your thumb should point right. Positive I. And then the opposite is K cross J. Yeah, I'm gonna share that with everyone else too. That's a good point though, Hudson. But I wanted to get the look. I mean, if the hand thing is confusing to you, I learn it. You know, we're taking physics, right? And this isn't physics. This is math. But all of this stuff is confusing. Okay, all of it is. And if I tell you need to learn something, you need to learn something. Because it's not just going to be in my class, it'll show up in Dr. Goldman's class, it'll show up in Dr. Koenig's class, it'll show up in Dr. Stolby's class, right? So you got to learn the right-hand rule. And yeah, it's going to be confusing, but you got to learn it. I don't know what to say. It's hard to learn when we can't really see it. Dude, I'm sympathetic to the fact that learning on the internet is difficult, Andrew. I can't change that. I can't make this an in-person class. So there's a lot of places you can read about this and show us. Did you see what happened when I tried to show you? Look. Oh, no. I didn't want to do that. What did I do? I moved this thing off the screen somehow. Oh, no. Let's go. Oh, then take this off. There we go. Look, watch what happens when I try to show you. Okay. So if we want to do the last one, let's do this one right here. Let's do J cross K. So J is up, like this. K is this way. What direction is my thumb pointing on the screen that you guys are looking at? What direction is it pointing? Is it pointing left or right?
Left.
Okay, but that's not the right answer, right? You see the problem, Andrew? It's reversed on my screen. I can't really show you if my camera reverses the image. You got to just use your mind. Yeah, here's some nice pictures that people are linking. Those are all really good ways of doing it. There's a YouTube channel where you can go read about it. All this stuff is very learnable on your own. Don't cry about it, man. It's not that hard. It's just something you got to spend time with. Physics is not supposed to just instantly be understandable. You got to spend time with this stuff, right? Okay, I'm spending too much time talking about this. Let's go. So we've got all of these. I left out 3 kind of intentionally here. What would you get if you do I cross I? One? Okay, let's check. So our definition for what the cross product is you're going to take the magnitude of I, you multiply by the magnitude of the other one, and then you multiply by the sine of the angle between the two of them. What's the angle between I hat and itself? It's 0, right? So you get 0. Sine of 0 is 0. So all of these, j cross j and k cross k, all of these are equal to 0. All of these are equal to 0. In fact, in general, any vector cross product with itself is 0. That's another property. So now we know all 9 and what they give us. And now that we know what they are, and we've figured them out from like a graphical perspective, right? Now we can use what I think it was Hudson that shared this was using. There's a type of cyclical nature to this, which you can draw like this. And the way it works is basically, if you go I cross j, you get k. If you do j cross k, you get I. And if you go backwards, you get negative. So anytime you go backwards, you get negative. So if you do k cross j, you get negative I. If you go I cross k, you get negative j. So when you... Is that right? Yeah. That makes sense? When you go clockwise, I to j to k, or alphabetical, you get a positive. When you go backwards, you get negative, right? I like to write it like this. Everyone writes things differently. So write all of them out like this. And when you go forwards, it's positive, and when you go backwards, it's negative. It's alphabetical, but it's like cyclical, right? So I cross j is k, right? So if you go I cross j, you get k. K cross I, you get j. But if I go backwards, I cross k, I get negative j. So there you go. That's one way you can do it, as long as you have the cross product stuff. But I want to emphasize, you don't always have these. Most of the vectors you're going to have in physics they're not going to be written like this. Most of the vectors in physics are going to be written like this problem. So that's why you have to learn the right-hand rule. There's really no other choice. I mean, you can find some other way to do it if you want to. That's just the way we've been doing it for a long time, and I think it's a pretty good method. So, all right, so let's get to the part about this that's a little bit harder. It's 2:55. We probably won't go into as much detail about this as I want to, because I want to move on to equilibrium, but what we can do now is we can ask the following. Suppose that I have a vector A, and let's say that it's written out in unit vector notation, like this. And I have another vector written out the same way. And we want to ask the question, how do I now find what A cross B is? Can you not replace IJK with ABC? I don't see why not. I mean, you can call them whatever you want to. Okay, so here's what we have to do. We've got each of these vectors. I'm just going to copy paste them in here. Got that one. We're cross producting it with the B vector, just like this. And that would be what A cross B is. And in order to do this, what we have to do is we literally have to multiply every single term out. Every single term. Except for the terms that are 0. Okay? So we know... I should really write out every single term. But I don't know that I will. So basically, if I do the first terms, this one and this one, I cross I, can you all see that that's going to give me 0? If I multiply the first two terms here? Okay. So I'll write it out just because I think it helps to see it written out. But it's AX, BX, and then you do I hat cross I hat. All right, what else do we have? Plus. We need to do the J one. So we'll have AX, BY, I hat cross J hat plus AX, BZ, I hat cross K hat. Okay. Do we want to do every single term? I guess we do. All right. So we're gonna have now we do the AYs. So AY times this one will be AY BX J cross I. Yep, it's a lot. It's pretty tedious. A, Y, B, Y, J cross J. You know, that one's 0. And then A, Y, B, Z. And that's J cross K, right? You would recommend doing it this way? Sometimes you have to. I mean, like in your homework, I know that one of the problems you have to do this. Okay, finally we need to do the Z terms. So we're going to have AZ, BX. I'm going to go do these one at a time. So it's going to be AZBX, it's going to be AZBY, and it's going to be AZBZ. And ZX is going to be KI, K cross I. ZY will be K cross J. And ZZ will be K cross K, right? Plus. There we go. Ah, it's just algebra. Yeah, pretty much. Vector algebra, I guess. Now, let's write our little rule right here. IJK, IJK. And let's write them all out. Let's get rid of the 0 terms. So anything that has I cross I, that's a 0. J cross J, that's a 0. K cross K, that is a 0. In addition, let's see, what's IJ? IJ is K, so I cross J is going to be K, so we're going to have an AX BY, and it's going to be multiplied by K hat. Now what I'm going to do is I'm going to open a parenthesis because I know, okay, I've done this one, I'll just mark underneath that we've done it. I know that this one, J cross I, JI going backwards, we get K, right? So there's also going to be a negative term, which is going to be this one, AYBX. Okay, so now we've done the two terms that are underlined there. And there's also going to be a J hat term, and there's also going to be an I hat term, like this. We're grouping terms to make things go a little faster here. What is the J hat term going to look like? Well, it's going to have to come from stuff like I cross K. But is I cross K positive or negative? Is I cross K positive or negative? It's negative, right? So that'll be my negative term, AXBZ. Where's the other KI term? It is there. That's going to be my positive one, right? KI is positive. So you go AZBZ or AZBX. And finally, for I hat, it's the remaining terms. That must be JK, which is here, and KJ, which is here. J cross K is going to be the positive one, so we go AYBZ. And then minus KJ is backwards, right? So we get a negative AZBY. And then we'll just check to see that we didn't make any mistakes. So XY, positive. YX, that's backwards in alphabet, right? There's a negative sign. XZ is backwards. AYBZ minus AZBY, I think I agree with that. AZBX minus AXBZ is J. Yeah, that looks right. That's right. Andrew gives me the double ellipsis, indicating that he's frustrated with how quickly this is going. I don't know what to tell you. All this stuff is stuff that I'm presenting to you now, and you'll have plenty of time to go read about it yourself if you want to. I'm not going to pretend like this is simple. It's just, but at the end of the day, it's just algebra. It's a new topic. It should be hard for you. All right, so that's it. That's the answer. And my God, if that's extremely complicated, but there's tricks and ways to get around this. I'll show you one of the tricks, but there it is. That's it. That's the cross product. It's pretty complicated, right? Actually doing the calculation isn't so bad, though, because, you know, in reality, what you're going to have is you could have a vector A that could be something like 1i hat plus 2j hat minus 5k hat, for example. And then vector B could be something like negative 1i hat plus 3j hat minus k hat. And it is overloading, I agree. Yeah, I understand. These are all going to show up in here to give you your vector, right? I mean, it's going to take some calculation, but you can actually do it relatively, it's not really quickly, but see how quickly we can do this, actually. So our I hat term, we take AYBZ. What is that? So AYBZ would be AYBZ. That's 2 times negative 1, which is negative 2. Minus AZBY. Well, that's going to be AZ is negative 5 times 3 is 15. So minus negative 15. It's not super fast, but I mean, it's all you can really do. The J hat terms, right? AZBX. So what's AZ? Negative 5 times BX, which is negative 1. So negative 5 times negative 1 is 5. Minus. And then you do the other ones, which is 1 times negative 1, I think. AXBZ is this one and this one. So 1 times negative 1, so minus negative 1. And then there's a k-hat term. And the k-hat term is going to be here, AXBY. So AXBY, 1 times 3 is 3, minus 2 times negative 1 is negative 2. That's all you got to do. It's just numbers, right? I mean, it looks awful when you look at it like this, but at the end of the day, it's just numbers, man. It's just numbers, you know? A cross B equals negative 2 minus negative 15 would be 15 minus 2, which is 13. And I could have made a mistake here. You can all check my work if you want to. 5 minus negative 1 is 6. And then 3 minus negative 2 is 5, right? That's your answer. So notice that you get a vector, right? You get a vector. You got the same thing. That's really good to hear, because I easily could have made a mistake there. Yeah, I mean, it's a lot of work. How much? It's 305. Do you want to see the quote easy way? Do you guys want to see the quote easy way? I don't think this is any easier. I don't think it's any easier, but I'll show it to you. Okay. So this is the easy way. The easy way is you use another form of math that you may or may not remember called the determinant, which is a matrix. And you write ijk at the top, like this. And then you write your vectors down here beneath it. So our vectors were 1, 2, negative 5, right? 1, 2, negative 5. And then the bottom one is negative 1, 3, negative 1. And these bars basically mean take the determinant of this matrix. Now, how many of you do not remember? I don't want to know who remembers. Who does not remember the determinant? Because I bet a lot of you don't. I would assume you probably... Maybe you've never even heard the word determinant. Have you all heard the word determinant before? You're just learning it, Jonathan? Okay. That makes sense. You do remember. Someone remembers. I bet a lot of you don't remember it, but what the determinant says is basically this. If I have a matrix, okay, and let's use a 2x2 matrix because it's simple, and let's say my matrix is like this, X, Y, Z, A, or something like that, right? The determinant of this matrix is found by taking X times A, go that way, minus Y times Z. And for a 2x2 matrix, it is very, very simple. Yeah, if you only have 2, it's really easy. If it's I and J. Now, to take the determinant of a 3x3 matrix is a little trickier. And I'm going to show you my method, and some of you may hate it. I don't know. What I do is this. Okay, that's not going to be easy to... Let me just... So what I do is, I draw a line. Oh, come on. I draw a line down like this. And then I draw a line over like this. And what I get out of that is I hat in the corner. It's going to have the factors of 2 times -1, which is -2, minus -5 times 3, which is -15. You take this kind of subdeterminant or something. I don't know what they call it. But you see how you get the exact same thing? 2 times -1 minus -5 times 3. So -2 minus -15. Was that easier? I don't think it's easier. You're literally doing the exact same thing. But
You have to write everything out.
it's like, I don't know. Okay, what's the next one? We're going to do k-hat next, because J is the one that's weird, and it's the one you're not going to like the way that I do it. Alright, J. Come on, give me this. We'll do k-hat next. Okay, k-hat, I just need to take this little bar here, shift it here, and now to get my k-hat, I do 1 times 3, which is 3, minus 2 times -1, which is -2. And that should be the same thing we got up here, right? Okay. What about the j-hat one? So for the j-hat one, I do something kind of... I don't know. People will dislike this or not. We'll see. So what I do for j is I noticed that I can't really do the same thing I just did, right? In the first case, what I did was I created a 2x2 matrix out of the bottom right and said that's my I-hat, right? For the k, I created a 2x2 matrix and I used the k up here, right? So what I want to do for j is I'm going to basically use a property of matrices. I shouldn't say that. I don't know if this is a property of matrices. I just know this works. I'm going to rewrite the first column right here on the left-hand side, or the right-hand side, like that. And that's going to be... This little box down here is going to be what I use for j-hat. So j-hat's going to give me -5 times -1, which is +5. See, same thing as here. Minus 1 times -1, which is -1. That's how I do it. What you may have learned in your math class is that you do 1 times -1 minus -5 times -1, and you flip it. You put a negative sign on the outside. That's the part everyone always hates. Because they say, oh, in math class, there's a minus sign in front of here. And I'm like, yeah, you can reverse things. It's the same thing. I think that in mathematics, part of the reason why they do it is because you can generalize it more. So as you go to 4-dimensional, 5-dimensional, 6-dimensional matrices, I think it makes it a little easier if you have this method of like alternating plus, minus, plus, minus, plus, minus. But we're never going to go beyond 3 dimensions in this class or in the 1 series, so this should be good enough for you. That is going to be one of the longer first sections of a class that we've ever had. I don't like going this long, and I apologize. It's almost exactly an hour. I'm going to stop the recording now, and I'll answer any questions that anyone has.